All right, off we go. I think I went a little fast in that last lecture, but today we'll do a lot of fun applications of flows and cuts. So hopefully it'll kind of reinforce some of the intuition. Uh, One point I want to make, which will be relevant for this lecture, but I forgot to make last time. So last time we talked about general capacities for flow, which could be real values and stuff. We showed, oh, if you do this shortest augmenting path, you'll still finish in polynomial time. One thing I forgot to point out, if the capacities are integer, okay, then each time you're going to push some integer amount of flow through the graph along some integer path. So at the end, your solution will be integral. Every flow vector, you'll end up putting an integer amount on it. And you could reinterpret it as, some number of paths if you wanted. Reason that'll be useful is now we're going to do lots of applications today where an integer interpretation of flow is much more useful than a fractional one. Okay, so you get that for free. If the capacities are integer, you get the integer solution for free, even though the algorithm is not particularly concerned with this. All right. Good. All right, applications of flows and cuts. So what I have set up is just like a handful of fun applications. Uh, what I'm going to do is I'm going to first present all the problems first. So you get one chance to see them all the way through and you can absorb a little bit. And then one by one, I'll ask you to figure out how to solve it. Okay. And this will be a whole lot of changing the input to the algorithm instead of changing the algorithm. Okay? And some of these you may have seen before, but hopefully not all. If we go fast, I have some problems loaded up at the end. Okay, good. So that's right, changing the input. All right. Okay, so this one I think we might have actually done together. This is not so interesting, but you could do vertex capacitated disjoint paths or something, right? We did this, right? Okay, so I'll skip this. All right. Yeah, forget that. Okay, good. All right, here's one. Bipartite matching. Okay, so I give you a graph, left and right side, so all the edges go from left to right, and you want to figure out the maximum number of disjoint edges. You're trying to take a lot of edges, but they can't share any endpoints. Yeah? What's the best matching you can get in this graph? Not a rhetorical question. 7? Uh, really? Yeah, disjoint edges. And you kind of think of matching left to right. 7 will be amazing because there's only 6 on each side. First day back. Well, it depends on if you're paying attention or not. I'm not sure actually, because sometimes I delete like 1 or 2 edges, so I can't tell you if it's exactly the same. But they definitely come from the same genealogy. One was copied and pasted from the other a long time ago. But then, nature happens. What you get? Anyone get 5? Anyone get 6? All right, I'm going to point to the edge and you tell me if I should take it. All right, can you see how that's highlighted? Yeah. Should I take this one? Okay. That means I cannot take this. I can't take this. This is sort of not very good, actually. Maybe I'll just use a pen. Okay, so I can't take this. I can't take this. I can't take this, and I can't take this because I've already used those endpoints. Okay, how about this one? Yeah. Okay, we'll take this. Okay. So I can't take this, and I can't take this. How about this one? Okay. So I can't take this. Can't take this. All right, how about this one? Okay. Can't take this, can't take this, can't take this. And this one, okay, I can't take this. Okay, so that's 5. The only question is, could we have done 6? Ah, okay, so out of these 3, I can only ever match 2 of them. Okay. All right. Uh, good. Oh, sorry. All right, next question is called vertex cover. We've done vertex cover before, but this is now in a bipartite graph. Okay. So the goal is to take the minimum number of vertices while matching or covering every edge. You got 5? Uh, okay. How'd you get 5? Which bottom 2? Bottom left 2, top right 3. This covers all the edges, we think. Yeah, there's no edges going from this section to that section, so seems to be okay. Okay, there's a vertex cover of size 5. What does that mean relative to? So you have to take at least one endpoint from every edge in your matching. So matching is always at less than or equal to vertex cover. So here you actually have proven them to be optimal. Okay. All right, that's another problem. Okay, here's a cool problem. This might be harder to eyeball. All right, this is called project selection. So you have a bunch of projects, okay, and they're generally profitable, but they may depend on other projects, which maybe cost money or something, right? So in this example, like this one's worth 6, that's a lot, but you would have to also commit to doing this one worth 2, and you'd have to do this one worth -5 and this one worth -3 in order to pull it off. Okay, so if you take something, you have to take all its dependencies. Okay, so your goal is to choose a subset of projects that includes all dependencies and maximizes the total profit. Yeah, what's the best you can do here? 2? How'd you get 2? Just 4 and 6. So you'd have to go like this, I guess. 12 minus 10, that's 2. Can anyone do better? Okay. All right, but at least you get the idea. Okay, next one is called playoff elimination. That was a commercial from probably before you're born or something. Okay. All right, so this is a sport called baseball. Okay. And you have 4 teams in which conference? Yeah, but which part? These 4 teams are in which division of baseball? MLB is the whole league, but does anyone know the subdivision? Ailey. Okay, good. The guy from Philly. Okay. So New York, what's their team name? All right, Baltimore. Okay, you know. Let's see, everyone knows. Toronto. Huh? It is really close. Not the Raptors. Blue Jays. Okay, Boston. Red Sox. Okay, so I'm a Red Sox fan. And okay, so the idea is, you're getting really close to the playoffs. Each team has a certain number of wins, and they also have a certain number of games played and games left to play. Okay? And the question is there any possible set of outcomes by which Boston can, at least tie the Yankees and sneak into the playoffs? Yeah, so the goal is just a tie, and then they get a wild card game or something. Okay, but uh, it's relevant who plays who. right? So if you just looked at this and said, if everyone loses and the Red Sox win all their games, then you'll get 92. But it gets trickier if they're playing each other. So in this remaining schedule, the Yankees are playing the Ravens and the Blue Jays once. Baltimore is playing New York. Okay, so you have this grid, and you have to look at this grid and say, okay, is it possible? Let's say even Boston wins all of its games, but now depending on how the other teams play out, is there some outcome by which Boston can win? Good. Um, that's another problem. Okay. Here's another problem we'll discuss. I think this actually motivated a lot of stuff in like World War II. But basically, you have a bunch of individuals and you have a bunch of jobs, and you want to assign people to jobs. Okay. But of course, not all people are qualified for all jobs. So maybe you're given as input some kind of qualification matrix. Uh, so the first person is qualified for the first three jobs. It's depressing that I drew jobs as a square, but it's okay. And so forth. Obviously, the last two people are both only qualified for the same last job, so you're not going to be able to allocate everyone, right? But depending on how complex the matrix is, this could be a more interesting problem. Yes, I think they were trying to assign like people to like big boats on D-Day and stuff in the old days. Okay, here's yet another problem. It's called edge orientation. I'm going to give you an undirected graph, okay? And your goal is to make it a directed graph. So every edge you're going to point one direction or the other. And you want to minimize the maximum in degree. So you don't want any vertex to like take in too many edges. It's like a load balancing problem. Okay, so you want to minimize the maximum in degree. Okay. So, for example, this would be such an orientation where I just added some corrections. And I guess this achieves a maximum in degree of 3. Okay. All right. Um, Another problem that we'll do is called densest subgraph. Okay. So the density of a graph is the number of edges divided by the number of vertices. But now let's say, suppose I'm allowed to take any subset of vertices, and I look at the subgraph, which is just the edges between those vertices. I want to get the densest subgraph in the graph, right? So yeah, no, you can absolutely have cycles. You want to minimize the maximum in this, so you want to make it small. Yeah. All right, so a densest subgraph, you want to choose a subset of vertices so that it's dense in terms of number of edges among those vertices divided by number of vertices. Yeah. Yeah, within. So it has to have both endpoints in your set. Yeah, so they want to do this when they analyze like social networks to find little communities or something, whatever. All right, anyone see the densest subgraph in this one? Yeah, so there's a click on 5 vertices in the middle. Yeah. So good. All right, so that's a whole bunch of problems. And now comes the fun part of figuring out how to solve them. Okay. Good. All right. Bipartite matching. For context, we just did flow. So basically, your goal is to figure out how to use flow to solve some of these problems. So, or edge disjoint paths. So I give you this undirected bipartite graph. You want to come up with an algorithm for the maximum matching. Yeah. Okay, so first, flow problems need a source and a sink, so that's what you suggested. And you want to connect the source to everything on the left, like this. And you want the sink to be connected to everyone on the right. Okay, and then what was the next idea? Yeah, capacity of one. And that's really modeling the fact. So I think you're imagining flow going from left to right. And the capacity of one is modeling the fact that I'm only allowed to use each vertex once. Okay. And same with the sink edges. Okay. Not quite done yet. Yeah, so we need to make sure everything is directed. And we should probably come up with capacities for them as well. One. Okay. I think infinity would also work. Okay. So, right. So we'll get some kind of graph that looks like this. Okay. I've oriented everything from left to right. I guess I forgot to draw arrows on the source and sink edges, but hopefully that's clear. Uh, and now you have to start doing some kind of if and only if proof. Yeah. So you want to say, okay, suppose I have some matching with, some number of edges, right? It's not the best matching in the world, but you need to show that this corresponds. So you want to show that what you probably have in mind is I'm going to build this graph, run flow. If the answer is 10, I'll say there's 10 edges. Okay. But to do if and only if, we need to map back and forth. So let's say you had like a matching, those four edges matched. What will be the flow of size 4? Just connecting the S and T. So nothing too special. So you'd kind of go like this. Okay. And then be careful to point out, well, I'm still only using each edge once, so it's feasible and things like this. Right here are my 4 paths and no edge is getting used twice. And then conversely, you say, oh, suppose I have a flow of size 4, or if, 4 edge disjoint paths. Okay. In fact, your homework will make clear that your flow of size 4 can always be turned into 4 edge disjoint paths. Okay. But then you have to extract the edges. So how would you just, maybe it's too obvious, but someone just give it a shot? Yeah. Yeah. So I think maybe one preliminary observation would be helpful is that every path from S to T looks like this. Goes from one to a vertex, across, and back, right? Establish the format. Just make it clear you can't zigzag, which you can't because you've added these arrows. And then once you have this format, oh, it always goes starting edge, middle, end, then we can remove the middle and, it's edge disjoint. I mean, the vertices will be disjoint because those capacities, one on the right, and you just kind of check some boxes. Okay, so usually the proof is just to double check your work more so than to develop your ideas at this stage. The other ones are more subtle, but maybe for this problem at least. Okay, how about vertex cover? Minimum vertex cover. Okay, so you say, oh, let's start trying to make the same kind of graph. Okay, so maybe I'll just go back here. Okay, so you look for the minimum ST cut in the graph, and that's at least pattern matching in the sense that vertex cover is supposed to be the dual of matching. ST cut is supposed to be the. Okay, so let's say you get some cut, right? Um, so uh, so one tricky thing is that, well, I'm not sure. It doesn't have to be an optimal cut. Uh, so maybe a cut looks like this. maybe red is hard to see. Um, start going over this in purple. So you delete these. This is not the minimum cut by any means, but you should still be able to rip out like a vertex cover or something, right? Now these edges from S and T, it seems like, oh, I should interpret that as this or something, right? That seems natural. But what a little bit awkward is like, how do I interpret getting rid of a middle edge, right? So this would be an ST cut in the graph, and we want to pull out a vertex cover of the same size. But I think there's slight awkwardness where I kind of know how to interpret those auxiliary edges on the sides, but it's a little unclear what happens if the minimum ST cut involves some of these edges in the middle. Ah, okay. So we can duplicate. There's even more direct way. Yeah. Oh, we can also make the capacities infinite, which will be very similar, but won't increase the size of the graph. So if you make this plus infinity, then any ST cut will have to only use those side edges. Okay. And now it becomes much easier to interpret. Oh, if you remove these and these, I'll interpret that as this vertex cover. Well, or at least this set of vertices, right? And now you have to prove that the thing is actually a vertex cover, which in this case it actually isn't, right? Because you want to show that, so this would be an unmatched edge here, right? So it seems like a vertex cover would need to like also have this one or something, okay? So now when you want to do the proof, right, you want to show that your ST cuts correspond to vertex covers, okay? And then you already know that the matching edges correspond to paths. So some level you want to say, okay, let's say I have an ST cut and it has to be of this format, and I want to show this is a vertex cover. Say, well, if there isn't a vertex cover, there's some unmatched edge. So let's say before I made this correction, if it isn't a vertex cover, then there's some edge that's not covered, okay? But then I also have this path, and so it wouldn't be an ST cut. So that would be maybe a proof by contradiction, okay? And then vice versa, if you have a vertex cover, you want to show it's an ST path or ST cut, right? Say, well, if it isn't, uh, then I should be able to find an ST path. All the ST paths have this format where I go left edge, middle, right, and that edge in the middle must not be covered if I'm able to get across. So it could be a little boring, but you just go and you double check the things. Okay, good. Um, great. All right, this one's trickier. Okay, project selection. Any ideas for how to do project selection? I think this one's substantially trickier, but you all are very clever. Yeah. Um, okay, so uh, I turned the vertices into edges. Okay, so first maybe I should add a source and a sink or something. And okay, let's take this 6 guy. When I want to turn him into an edge, what do you have in mind? Okay, so all of these will, oh, like this. Okay, this will be 5. Oh, well, what does a negative capacity mean? Okay. So your logic is like 4 minus 2 is 2, so I should think of this as 2. And then 4 plus 6 minus 3 is 7, so I should think of this as 7. One slight concern is that this doesn't capture the fact that they're sharing the same 4, right? Or depending on how you're thinking about it, but those numbers don't encode the fact that they're actually sharing and you're double counting some of the good stuff. Yeah, sure. Well, you always cleverly phrase your answers as couldn't you? The concept of a plan. Uh, okay. So it is actually going to be an SD cut thing. Yeah, it's very unclear I mean, the -5 is quite unsettling, right? Peter, do you know the answer? Have you done this one before? Anyone want to take a wild guess as to how to set up the sink edges? Yeah. Yeah, so we're going to interpret the negative edges like this, okay? And then the positive projects are going to have edges from the thing. So, all right, so what's going on? So the high level idea is something like if I fix some kind of ST cut or something, then, so for example, this cut, you're paying for the edge, the projects you take. So every project you took, since T is on the other side, going from S to T, every project you took, that edge is going to go to T, so you're going to pay for it. Okay. And then as far as the good projects go, every project you leave out, you also pay for. Right? So at some level, you want to maximize profit, minimize expenses. So you can see on the right how it's trying to not pay for expenses. And on the left, you can see that, well, every time I give up a project, I also give up that value. Yeah. No, you do. So this would also be bad. So we haven't quite figured it out yet, but at least can you see at least that part of the logic, which is that the minimum ST cut will want to keep the green on your side because every time it puts green on the T side, you lose that money and it goes into your cost of your cut. And it would also prefer to put the cost on the opposite side because whenever you take a cost project, you pay for that because you're trying to minimize the edges you cut. Okay? Yeah. Yes, I shouldn't be able to go I shouldn't have 6 to 2 across the cut because if I take 6, I have to take 2. So let's make it really expensive to do that. How expensive should we make it? Yeah, $1 trillion. Okay, so we'll make this positive infinity. Okay, so that means that any, finite ST cut will never violate a dependency. So, uh, uh, so this would be okay. Okay. This looks a little weird because it looks like you have an edge going from 3 to 2. But that's okay because that's going from the T side to the S side. We're only counting the edges going from the S side to the T. Okay, so here I don't think we're violent. Oh, no, okay, this is still wrong. Uh, sorry, that's why you guys are looking at me weird. Or only the latest reason why you're looking at me weird. Okay, so this would I think be okay. Okay, now we're not there's no infinity edges across the S to T cut, although there's one in the opposite direction. Oh, you mean just like what are the rules of the game? No, it's just counting the edges that are going from one side to the other. So reverse edges don't cost anything, no. Like think about it. So yeah, imagine you're doing the ST cut problem and there's some bottleneck, I can't really send more flow across this cut from S to T. Adding reverse edges doesn't really matter, right? From constraining how much goes forward. Adding reverse edges, who cares? Absolutely. Yeah. Yeah, undirected graph, no. Directed graph, yes. Well, like, what do you mean positive? You mean these red circles? So like the two, for example, is 5 or -5. Yeah, negative numbers become sink edges. The positive numbers become source edges. Dependencies become infinity. Yeah. So I think we just need to do okay, so now we just need to formalize that the minimum cut corresponds to the best project selection. Okay. But it's a little bit weird, right? Because we're not just like adding up. Let me restore this. Damn it. Okay. So the size of the cut here is actually 3 plus 5 plus 3 plus 2. So there's 3 on the left, and then there's the 3 edges on the right, which doesn't directly give you any cost of a project selection, right? So how do I actually map this? From what? The total green. So let's say, oh yeah, so total, yeah, I'll write it that way. I guess total, yeah, I guess possible profit, minus, which is sort of that min ST cut, or maybe I'll just write ST cut for this because this is for any plausible thing, is equal to the net profit of the projects you select. Okay, so then you just have to be a little more careful than this and go back and forth. Yeah, but you just have to be a little careful because you have to interpret it based on this shifting. Okay. All right, so that one is clever. Good. All right, now let's do the playoff one. All right, so here, right, can Boston catch the Yankees? Oh, it says Yankees. All right. Okay, so you have something like this. So I tell you who's going to play who in the remaining games, and you're trying to figure out if it's possible for Boston to make it into the playoffs. So in this one, is it possible? So I guess in this one, um, you can assume Boston wins both of its games, and you need to make sure the Yankees lose. So where the win gets assigned to the person on the left. Okay. So at this stage, everyone has 92, but now you have somebody has to win this game, and that'll put them over the top. So in this case, it's impossible. We just want to figure out how to do this automatically. Yeah. Yeah, tied is good enough. Oh, yeah, yeah, that's right. Tied for the lead. Yeah. Yeah. Okay. So somehow I think you're thinking like, so flow is a little bit of an allocation problem, like matching is an allocation problem, right? And so we have these wins we need to allocate. And each game needs to go to one of the two teams that play in the game. And I want to somehow allocate the games, hopefully so that everyone has at most 92 or something, right? So, okay, so I think what you're thinking is something that kind of looks like this. So I have a node representing all the games in the first column, and then all the teams in the second column. And each of these games is one win that I have to distribute. So I left out, well, I guess it's okay. Something like this. And so New York versus Baltimore, that has to go to one of these two. New York versus Toronto has to go to one of these two. Toronto Raptors. I got it wrong. Okay, something like this. Yeah. And what should I put for the sink edges? So there's no capacities on those edges for the teams to the T. See? All one? So you're saying, oh, New York's allowed to win at most one? So one thing we can do is say, oh, what's the best Boston can do, which we know is 92. And then that means the remaining teams, New York, I don't want them to win any. I can allow Toronto and Baltimore to win at most one. In Boston, I just want them to win as much as possible or something. So I'll leave an infinity. 90 wins. It's 180 games in a year, so they're all close to 500. Because for those of you who have played football, football will give you a very big headache. You don't want to play too much. But you didn't know baseball had 180 games? Yeah, 182. And they only play for half the year, so it's every day for a long, yeah. Yeah, they'll go to a place and they'll play 3 days in a row. Oh, how many of you have been to a baseball game, a professional baseball game? Okay, some of you. Uh, okay. How many of you have watched a whole baseball game on TV? Amazing. I played Little League. Yeah, I mean, I think it's a different time, but definitely I can see why football you don't play more games because you'll just die. Uh, yeah, it's a different. Anyway, uh, okay, so that's why there's 90-ish wins. uh, in this case. Um, yeah. This kind of problem also works for football though, with smaller numbers. Yeah. Okay. And I guess we need to figure out what to do in the middle edges. I think there's many possibilities. We could just put a 1 here because at most one win is going to get allocated. Okay. All right. So once you set up this graph, what would you do? Yeah, you'd run flow and see if you're able to get a flow of size 5. It's going to try to push the winds through uh, without, exceeding this upper bound for all the other teams. So if you're able to do 5, then you should be able to read off this assignment. Oh, each game got assigned there and there and there, and New York got 0 of them, and Baltimore got 1, Toronto got 1, and Boston got however many. Sorry? Uh, maximum flow. The maximum flow is not 6. What's the maximum flow in this graph? You can get 5? 5 is an upper bound, but if we got 5, then that means we'd be able to find a way to get Boston into the playoffs. Because you're able to allocate all 5 wins while only giving 1 each to Baltimore and Toronto and 0 to New York. So for us, I think it's 4. But we should be able to figure out the cut. Well, it's just an upper bound. Uh, yeah, so 2 would also been fine. Yeah, so we're not able to route 5 units of flow through this graph. We should be able to find an ST cut of size 4. I guess New York you get for free. Right, so we can take this edge. That costs 0. Right? And then in the 2 Boston games. Oh, sorry. Okay, so that will be a cut of capacity 4. So 0 capacity edge is sort of like not having an edge there. Okay, so that will prove to you. We shouldn't be able to get from SCT in the remaining graph. Okay. So for this problem, you just want to read off, if it's possible for Boston to get into the playoffs and these are the outcomes, here's the corresponding flow, double check that it's a flow. Conversely, if there's a flow of size 5 or whatever the number, then I can read off these outcomes and yeah, it's a little cumbersome, but it's okay. Make sense? Okay, good. We're having fun, I hope. Yeah, something like this. Okay, maybe this one's not too tough. All right, the assignment problem. So your input's really some kind of matrix, and your goal is to try to fill as many of the red cubicle jobs as possible with individuals. Okay, so uh, I guess you have something in mind like this. S, T, individuals and jobs, which means you're going to set up the same graph. Everybody wants a job. Every job wants to be occupied. And then here is where you start looking at the incidence matrix, which people are qualified for which jobs. Okay. So this is like a very simple allocation problem. Okay. But if I, for example, said, oh, some of these jobs are different. Maybe this job can take in at least 3 people. This job can take in at most 2. And this person can handle 3 jobs at once or something. Yeah, pretty amazing person. Um, how could I adjust my graph for this? Yeah, so I can say, oh, this person can handle 3 jobs, so I'll allow 3 there. This job can take in 5 people, so I'll put a 5 there. Okay, pretty flexible. Sometimes this is called B matching, where you have these B values on the vertices. Okay, good. Yeah, nothing special. All right, edge orientation. You try and direct all the edges in the graph to minimize the maximum load. Yeah. Okay, so you're imagining an assignment problem. So one side is edges, one side is vertices. Okay. All right, so yeah. Okay, so uh okay, so ignore this for the moment. Uh so imagining something like this. Um so okay, it's a little bit hard to see, but I'll zoom in. So each of these represents one edge in the graph that's sort of in a slightly darker blue, and it has edges going to its 2 endpoints. Okay, something like this. Something like this. Okay. Now, I imagine this would be capacity 1. So each edge needs to be assigned to one of its endpoints. That's like orienting the edge. But what should I do to source and sink capacities? So you can do binary search on what's capacity? Like capacity of an edge or like the target you're going for, this min max. Yeah, so then what we're going to do is we're going to take some guess H, which is sort of that min max target value. Okay. So now you're just trying to say, oh, is there a way you're solving a decision version? Given some value H, can it orient the graph so that every vertex is in degree at most H? And if we can answer this yes, no question, then we can binary search. Oh, no, let me lower H. Yes, let me increase H. Okay. You know it's going to be some, rational value, so there's only a polynomial number of choices. Okay, so that's what you do. So that means where should I put the H? On the sink capacity, because each vertex can only take in H edges. Everything here will be 1. Okay, so it looks something like this. Okay, and so now you just have this yes no question. If you can orient, then that's going to for each edge choose one of the endpoints, and you should take those corresponding edges. And conversely, if you can route, well, yeah. So what should I actually do for the algorithm? So I build this graph. I want to answer this yes no question. I run max flow, I guess, and then what? So it outputs some value, yeah? HN. So HN, yeah, so you're going to say, oh, is the max value HN? If so, I say, yes, you can orient. If not, no. So, okay, so you run max flow and you get some value. So what should I do? I compare it to HN. Oh, you can compare it to the number of edges. So in particular, you can see if you're able to orient all the edges so it fits into this HN stuff on the right. So if you are able to get a flow of size M for edges, then that means for every edge you're able to find some way to get it all in. Conversely, if you have an orientation, so for every edge you're able to assign a direction, then you should be able to reconstruct this flow. Every edge is only getting used once. And on the right side, because the orientation had max degree h, you should be able to fit it into capacity. Okay. All right, good. So edge orientation is just another assignment problem. All right, how about densest subgraph? Yeah, that will give you a factor two approximation. Yeah, I gave a talk on this. I don't remember if you were there, but yeah. Actually, the guy who kind of invented it is actually giving a talk tomorrow. We have a colloquium talk. Was well, in this case, I have to go. How do you find it? Well, we have these posters around. Okay, good question. Okay, where do you find it? So first we have all these faculty interview talks. Huh? There's an email list. Sometimes there's like a faculty calendar on some website, Purdue CS website. So tomorrow's one of the distinguished lectures. So I think it's broadcast everywhere, including there's little posters on the wall in Lawson. It's at 3 o'clock ish. I think it's at 3 in probably our biggest room, probably in Lawson in that big room. And I think there will be like snacks after, so you can come to that instead. Uh, no, but that's Moses Charikar. He's a good theory guy, but he actually was the first to analyze that two approximation. It just happens that he's here from Stanford. The two approximation, by the way, no, your goal is to try to identify this graph here, right? And you might ask yourself, well, what's the least likely vertex to be in a dense subgraph? Well, let me take the vertex's minimum degree. Say, this is probably not in the graph. That's probably not in the graph. And you just repeatedly keep peeling off the vertex's minimum degree remaining in the graph. So that's degree 3, degree 3, any degree 2s? No, degree 3, degree 2, degree 2, degree 3, degree 2, degree 2, degree 2, degree 2, degree 2. So you keep peeling off these vertices that have the smallest degree remaining. And then you look at that graph, what's the density? The next one, what's the density? What's the density? And you choose the best graph you run into over the course of this process. So this algorithm will keep going past this point. Oh, I'll delete this and so on and so forth. But it will look at that whole sequence there. What's the best I found? That'll actually get you a two approximate densest subgraph. And because it's very simple to implement, I mean, I literally just did on the fly. It's popular in practice. It's only two approximation though. That means you'll get that your solution will have density at least half of the optimal density. I can give her homework. I mean, it's very cute, but it's not that related to flows. But it's a very nice algorithm. Okay. Anyway, that's a two approximation. But you're trying to get an exact algorithm. What if you were looking at the decision version? So I give you a value h again. You want to know if there is a subgraph of density at least h. Okay. So this one is actually turns out to be dual to the edge orientation problem. So if you look at that densest subgraph here in the middle, so the density is what? How many edges are there? 5 choose 2. What is that? 10, and then there's 5 vertices. So you shouldn't be able to orient it so that there's more than less than 2, right? The density alone gives a lower bound on the max in degree. So if you set up the same graph, okay, uh, you will find when you get the minimum ST, okay, if there's a subgraph with density greater than H, then you shouldn't be able to saturate this flow. You shouldn't be able to orient all the edges because that dense subgraph itself won't be able to handle that orientation. You won't be able to orient the densest subgraph, right? Because the average degree is already bigger than H. So, well, maybe we can skip it. But what you want to show is the following. If the max flow is M in this graph, then all subgraphs have density at most H. Okay. And if there's a subgraph with density at least lambda, at least H, then you're going to get an ST cut of size less than M. Okay, you guys look a little tired. Okay, would you guys rather do this proof or do exercises? Like funner exercises? Oh, well, the whatever the solution is a rational number, right? Because it's edges divided by vertices. So you can ultimately binary search for. Yeah, because the numerator is one of poly n values and the denominator is one of poly n values. So number of possible fractions is polynomial n, and log of polynomial n is log n. All right, let me see if maybe an exercise would be more fun. What would be a fun exercise? Yeah, does this look really long? All right, you want to do this one? This one's fun. Okay, but I think I wrote extra because, it was an exam question or something. Uh, okay, let's try this one. This is the n-Rooks problem. Okay, so I give you a board, and some of the squares are marked off as, unallowed. And your goal is to place, n by n board, and your goal is to place n rooks so that they're not attacking each other if it were chess. So each row and each column has exactly one rook, and some of the possible places are blocked out. No, the rook can't. You can't put the rook there. The rook can still see over. Okay, how? Assigning between one and what? Okay, so you want to make a bipartite graph with rows and columns, I guess. So each vertex will represent a row, and each one on the right will represent a column. Is that the idea? Okay. How? Okay. Okay, so if I'm allowed to put a rook there, I'll put an edge. Something like this. And then we'll set up our usual ST kind of thing. Okay, so what's the idea? Huh? Not blocked is what I meant to write. Like there's no X. Yeah, so a rook occupies its entire row and its entire column. Okay. And so each of these edges in the middle represent a place where you can put the rook. Okay. But you can only have one rook in each row and one rook in each column. There's some places you can't place a rook at all, so you omit those edges from the middle. Okay. So yeah, this does turn out to be an assignment problem. Yes, and then you're going to see if you're able to saturate all of the rows or all of the columns, then you're able to get a rook in every row and a rook in every column without having two in any single row or any single column. Yeah, there's like a more painful version I can think of with bishops, but it's okay. Yeah. Does it work for the n queens problem? Uh, well, what do you guys think? Yes, there you have to do is rows, columns, and diagonals. That becomes more painful. Huh? Yeah, so maybe I should mention, is this true? I mean, well, the following problem is NP hard. So instead of a bipartite graph, I give you a tripartite graph. Okay, here's some vertices. I don't quite remember how to prove this, but we can do it if you want. Okay, now every edge, instead of being between two vertices, is between three vertices. Okay, that's one edge. So each edge has three endpoints, one from each part. Sometimes it's called a hyperedge, but that's a silly name too. Okay, but now you're trying to take as many of these triplets as possible with the vertices being disjoint. This is called three matching, and this is NP hard. We could probably think of how to prove it if you wanted, but it's one of the classical. I think it was in the original paper. Sometimes when you go from two to three, things change, just like two sat to three sat. So I think we can try to go from here, possibly. Oh, is that obvious? Trying to figure if you can go from this problem to n queens because you have rows, columns, and diagonals. Huh? Okay, there's two diagonals. Oh, the floor matching should be hard too, but one would have to do a little more work. Okay. Yeah. Well, yeah, there's some variants of scheduling you can do and some variants of scheduling that become hard. But yeah, many variants of scheduling are NP hard. So yeah, so some assignment problems, but these are all natural problems. I mean, people want to do scheduling, people want to do, they don't really want to place n queens, but they do want to do a lot of scheduling or assignment problems with some constraints. Some problems, for various reasons, you can solve, especially if they can be turned into flow or some slight extension of flow that we won't necessarily cover. Like combinatorial optimization is full of all these problems you can solve, but then there's a lot you can't solve either. Um, in fact, you can argue that P versus NP stuff kind of killed combinatorial optimization to some extent, because there was a time where we thought maybe with some clever ideas we can solve everything. And so it's quite disappointing to find out that most things maybe we can't solve in this satisfactorily polynomial time kind of way. Okay. All right, since that one went too fast. All right, let me try another exercise then. All right, this one is called cycle cover. Okay. So here, I give you a directed graph. Okay. And your goal is to come up with a disjoint cycle to cover the graph. So what's a cycle? You know, it goes around in a circle. And so you want to cover all the vertices with cycles, but it should also be disjoint. Okay, so in this graph, like all of the edges, including the dash, would be the underlying graph. But you see, I have two cycles that cover the entire graph, right? So for example, maybe there's two versions of a problem. Is there a cycle cover? So you can choose as many cycles as you want. Maybe another version of the question is Is there a one cycle cover? Can you use one cycle to cover everything? I think, yeah. So either one, give us some thought. Yeah, so a one cycle cover is just a thinly disguised Hamiltonian cycle. Yeah, yeah. Still, I would have put that on an exam to see if I could get you. Okay, so one cycle cover is NP hard because the only way to cover everything was with a Hamiltonian cycle. Good. All right, but now you're allowed as many cycles as you want, but they do have to be disjoint. Uh, yeah, so SCCs don't tell you because they still have to be cycles, so you're not allowed to revisit 30. An SCC maybe it looks like a figure eight, right? But then you wouldn't be able to do a cycle cover. Yeah. Is it not? I thought these ridiculous solutions. Okay, come on. Okay, so every vertex needs to have in degree one. Okay, so you're imagining assignment where there's vertices that are receiving stuff. Okay, so I'm imagining this to be the right side of a bipartite thingy, is what you seem to be describing. So the idea is that, okay, each vertex should have in degree one or something. So I imagine it taking one. Well, what should be the left? Okay, edges. So it's true, but they need to be coherent, right? Like, uh, I guess not. Something like this. Yeah, I think everyone has out degree one there. Oh, they also have to have in degree one. Uh, so like another copy here. Is this, so this should be V, another. Okay. So is this something like this? So I have one set of edges, and I have two copies of the vertices, like this, is what you have in mind. And these all have one. So if an edge is like going from X to Y, then this should go like to X here, and then to Y here. Is that the idea? So one, one. So what should the source connected to each edge be? Two. So, okay, fine. So the idea is that each edge, I'm trying to route two units of flow and it would go to the two endpoints. But what forces the algorithm to actually, like, why doesn't it send one unit of flow to one edge and one unit to another, right? You can be kind of doing half of what we're intending. So the algorithm doesn't have to send two units of flow to that edge. It could just send one and use that to make X happy and not use it to make Y happy. You use some other edge to make Y happy. Merge merge the two vertex sets. Okay, so you want to add lots of capacity here, uh, between two copies of a vertex or something. So do you still want a bipartite graph? Oh, so I have my two vertex sets from before, and then I have something that glues them together before going to T. I mean, this looks a lot like E again or something, right? Because of all the pairs you're imagining getting glued back together. But there's still no reason why I can't just route one unit of flow and not route both. Guys are really close, of course. Hmm. You're just like reading my expression, I think. You guys are really close. You have to figure out, it is going to be a bipartite assignment kind of thing, but you have to figure out what to make the left side. And it's not quite E, because you tried E. I don't know what previous vertex means, but okay, what if we did also V? Where one node here represents one vertex in the graph. Yeah, so if there's an edge from X to Y, I'll add the corresponding edge in the middle, right? So now what's this trying to do is trying to send one unit of flow to each edge. And that edge, I mean, each vertex, and that vertex picks one of its edges, it goes somewhere else, and then one unit of flow goes out. So if you're able to do it, then every vertex will have one edge going out and one edge coming in. So everyone will have degree one. And if you have a graph in and out degree one, any graph where every vertex is in and out degree one must break down into cycles. Yeah, so now you see if you can do a max flow that routes all the vertices on both sides. So flow of size n, and that'll give you the cycle cover if it exists. So the homework, you have to just be a little more careful going back and forth. Yeah. How do you, so if we do it like this, each vertex will end up with in degree one and out degree one. So that forces the cycles to be disjoint, because if it shared a vertex, that'd be in degree two and out degree two. So just having in degree one, out degree one, actually, yeah, that's actually all that matters. And then the cycle cover is, some level of indirection as usual. Okay. All right. That was fun. We're past time, so we'll end there. Yeah. Okay, great. I'll see you guys Thursday.